Okay, so this is circular motion. We have to talk about circular motion today. Physics, chemistry, including mathematics, basics are always important. We need to understand what some of the things that are so applicable under the same topics or rather under the same courses. So here I'll talk about some basics that we need to understand, mostly the ground of circular motion. We have to know the ground of circular motion. Okay, so if we just get back a bit to kinematics, we are going to find that kinematics, that is the motion which involves the object moving in a straight line. This is according to kinematics. An object can just be moving in a straight line. Okay, but whenever we come to the issue of circular motion, an object takes a circle-like path. It keeps moving in a circular way. Okay, it keeps moving in a circular way. All right, so I remember in one of the videos that we recorded with other people, we talked of some definitions. We talked of acceleration. Acceleration, from this one, it is called linear acceleration. Some people, they say tangential acceleration. So it has to be called a linear acceleration, which is linear. Okay, then we also have velocity. So this also is called linear velocity. We also have displacement. This one also, under kinematics, it has to be called a linear displacement. Okay, but whenever we come to this type of motion, which is called circular motion, we are going to understand that for something to move from a given point, we are going to fully understand to say, if a particle, maybe you try to tie a particle. Let's say this is my string. I get a good example. If this is a string, you tie a particle to this given point. You understand that the length from this given point to where you are holding here, you can just measure this length and place it to be the length from where you are here to where the particle is going to be. To where the particle is going to be. All right. So if I catch at this given point, I handle it at this given point, my length from here up to somewhere there is going to be called the radius, which is going to be this one. It has to be called a radius. In that case, I mean something like that. So my particle is going to be located at this given point. You tie a particle to a string, and then from where you are, or from where you put your hand to where the particle is, this has to be called a radius. All right. Under linear motion, if an object moves from this given point to a specific distance or to a specific position, it keeps on changing due to what? Due to the position in short. So it will have changed in what? In position. And that is what we call displacement. Linear displacement. This also applies to circular motion. If an object is to rotate, it covers a specific distance and then it comes to this given position. It will have the same what? It will cover the same, or it will have the same radius. So the distance it takes to move from here up to somewhere there, it is denoted by the angle it covers at a given point, which is going to be here. And what name is given to the distance that it covers from here up to somewhere there? It is called angular displacement. It is called angular displacement. Why? Because it sweeps a certain distance by covering the angle which is given here. It sweeps this same angle for it to move from this given position to where it is. To where it is. Here we are going to find that the distance it covers to move from here up to somewhere there, it is measured in meters. Okay? But here, we're talking about the angle which is here, and this angle is the one which is called my distance. For displacement here, you can label it with letter X. I mean S, sorry. But here, you find that the angular displacement is denoted by letter or by a symbol theta. It is denoted by the symbol theta. So whenever you move from this given point to where the particle is going to rest, that displacement has to be measured in what? In meters. But here, if you sweep this given angle as the distance, you find that the path it is going to take from here up to where it is called an arc length. And also it is denoted by letter S. This is called arc length. So how do you find the same distance in reference to the radius where it is in reference to the radius that it has from the position where it is tied and covering a given angular displacement like that? How do you describe this, or how do you relate this radius to the arc length, including the angle which is given there? Okay, so it is very simple. For you to find the arc length which is here, we have a simple formula that we are going to be using. This formula has to go like this. You see, arc length has to be equal to r theta. So this is the distance it has swept, and this has to be the path that it has taken. That has to be a path that is it has taken. So someone can even ask a question to say, what are the SI units that we are supposed to be using whenever you want to describe what we call angular displacement? So we have three types of SI units. We have three types of SI units that we are going to be using for us to describe the what? The distance or the angular displacement. What are those? One, you'll find that this one, which is the angle, in other ways displacement. Here we are going to say we have the following displacement. The first one has to be radians. The second one has to be degrees. And the third one has to be revolutions. Okay. So according to standard way of dealing with circular motion, we are going to fully understand to say the most appropriate units here are supposed to be these ones. Are supposed to be those ones. Okay. So if we are to be given a simple example, let me put an example here. I'll say a stone is tied to a string of length 2 centimeters, sweeps and arc length of 10 centimeters, find the angular displacement. Okay, so whenever a question has come like this, what are you supposed to do? What are the things are you supposed to be doing whenever a question has come like a stone is tied to a string of length 2 centimeters, it sweeps an arc length of 10 centimeters, and are saying find the angular displacement. So we are going to look at this one, and I said the standard SI units to use whenever you are dealing with the angular displacement has to be what? Has to be radians. So meaning that if you want to deal with a simple thing here, you have to look at what arc length have you been given in the question, and then you also have to concentrate to say what is the radius at which the particle has been tied. Okay, so in a simple demonstration here, I'll say solutions. Okay, so we are going to have something like this. A stone is at this given point being tied to a string of length 2 centimeters, and then they're saying it has moved from this given point that given point covering an arc length of 10 centimeters. Okay, covering an arc length of 10 centimeters. So here I'll say, what information have you been given? What information have you been given? They're saying arc length has to be 10 centimeters, radius has to be 2 centimeters, and the angular displacement hasn't been what? Given. So how are these three quantities related to each other? How are these three quantities related to each other? Okay, so they are related to each other by saying arc length has to be equal to radius multiplied by angular displacement. Meaning that to get the angular displacement, you make it as a subject. Then theta has to be equal to, what is this? We have been given it as 10 centimeters. What is that? The radius is 2 centimeters, meaning that theta is equal to 5 radians. It has to be 5 radians. So that's how we do calculate for what we call the angular displacement. That's what we do whenever we want to calculate for angular displacement. Okay, now here there is a simple thing that we should always be understanding. Okay, there is just a simple thing that we should always be understanding. What is that thing? We need to know the relationship between kinematics and circular motion. We have to understand the relationship between kinematics and circular motion. Okay, but before I come to that, we have also to understand to say, how do we convert the so-called revolutions. Sorry, here we made a mistake. The other SI units, yes, quite right, they're supposed to be these ones, revolutions, yes. But whenever we come to the issue of, if we just look at this thing, we are saying acceleration, velocity, and displacement. Acceleration, velocity, and displacement. How are these quantities related to each other? How are these quantities related to each other? So I'll divide it like this. Okay, so I'll put a simple division which is going to show the relationship between circular motion and kinematics, and what are the conversions. Okay, so we have the following formulas. V is equal to V initial plus A T. V square has to be equal to V initial square plus 2A S. S has to be equal to V initial T plus 1 over 2A T. S has to be equal to, we are saying we're going to have V initial plus V final over 2 multiplied by T. Okay, so angular linear motion, velocity is denoted by letter V. Displacement is denoted by letter S. Acceleration is denoted by letter A. And time is denoted by letter T. So these same things, you'll find that here, under circular motion, velocity, which is called angular velocity, it is denoted by the letter called omega. It is called omega. What is that same letter? Omega has to be letter W. Okay, that is velocity. Okay, remember I'm saying V here for kinematics. Let me write kinematics. Then here I'll say circular motion. So V under kinematics, if you come to circular motion, it has to be changed to what we call omega. Acceleration, here it is denoted by letter A, but for circular motion, we are going to denote it by letter alpha, which is something like this. This is for acceleration. Okay, this is for what? For acceleration. All right. If we come to displacement, displacement here is denoted by letter S, but under circular motion it is denoted by letter theta. So this is going to be displacement. The same expressions I'm from dropping here will be the same ones that I'm going to write here, but we are going to change the letters that we have used here. Where there is V for this one, I'll use W. Where there is V in initial, I'll use WI to simply mean the initial velocity. Remember, this is linear velocity. Here, omega is said to be angular velocity. Same applies to acceleration. Here, this is linear acceleration or tangential acceleration, but here it has to be called angular acceleration. This is displacement, linear displacement, and here it is called angular displacement. So, like I said, where there is this one, I'll replace it with, so I'll say W, it has to be equal to, I'll say W initial plus, where there is acceleration for angular, I'm going to use letter alpha, like this. If you come to this one, we are going to have W square equal to W initial square plus 2. Where there is acceleration, we are saying we are going to replace with what? Alpha. Where there is displacement, here we are saying we have to be using theta. If I come to this one, where there is displacement, we are going to have theta, which is going to be equal to, where there is this, we are going to have initial t plus 1 over 2. Time doesn't change, you still use the letter t. So where there is this, sorry, here I forgot to put square. Where there is linear acceleration, we are going to have alpha, then I'll say t square. Then we are going to have t square. Okay, so those are the simple things. But we are not done. What are the SI units for velocity at this moment of time? You find that under linear kinematics, velocity v is given by SI units as meters per second. Acceleration is given the SI units as meters per second square. Displacement is given with the SI units of what? Meters. But here, we are going to find that I'm saying the distance, or rather displacement, is measured in what? Rads or radians to say. But time will be the same. That actually simply means for this given position, if you want to find what we call the angular acceleration, or I start with velocity, it must be measured in these SI units. Where there is distance which is measured in meters, for this one we are going to replace with what? Rads. So this is going to be measured in rads per second. Okay. If we come to acceleration, here it is measured in what? In meters per second square. Here I'll say alpha must be measured in, where there is meter, I'll use rads. Second will still remain the same. If you come to displacement, here we are going to say theta is measured in rads. It has to be measured in rads. Okay, now how do you convert the SI units? Maybe, okay, we are going to observe that here we are saying these are supposed to be the SI units, the actual SI units for what? For every quantity. Angular velocity, angular acceleration, and angular displacement. There are certain questions whereby they can even ask you a question which is going to be given in revolutions per minute to show that that is what the SI unit for this one. I know sometimes it can also be measured in what? Revolutions per minute. Remember the SI units that I just talked about for displacement here? I said it can be measured in radians, degrees, and revolutions. And this is displacement, the angular displacement. So since we are talking about angular velocity, meaning that it has to be measured in what? Rads per second, degrees per second, or revolutions per second. So whenever a question has come to say convert maybe 20 revolutions per minute into the actual units, they simply mean you have to convert the same thing into what? Radians per second. You have to convert those same things into radians per second. Let's try to have an example based on what I'm from explaining here. Based on what I'm from explaining here. So say convert the following into their actual units. Okay, so if they give you 20, revolution is mostly denoted by letters R, E, V, then they'll put minute somewhere here, that is A. B, if they give you something like maybe 320 degrees per second. Let's try to have these two examples. We try to have these two examples. How do you convert degrees into radians, and how do you convert revolutions into rads per second? So here, if I start with the first one, the relationship the way it is, we are going to observe that one revolution is equal to 2 pi rads. I'm saying one revolution has to be equal to 2 pi rads. So we have to avoid the system of converting things using these same conversions. Here, the standard way of converting, you have to concentrate on what we call a chain link. You have to concentrate on a chain link. And what does it mean if you have something like this? This, in other ways, it can also be written like 2 rads per revolution, because we are saying one revolution is equal to that one. Now, if you want to convert this, what are you supposed to do? Remember, we want to convert to the actual units. And what are the SI units here we are talking about? If you come across something like this, which is saying revolutions per minute, meaning that the SI units we are going to get are supposed to be rads per second. We are going to get rads per second. All right. A. So what we are going to do here is, if we come at this one, I'll write it like this. I'll say 20 revolutions per minute. You have to put minute down here. Okay, so what are you supposed to do for you to get rid of this? Look at the conversions we are from writing here. You are going to put revolutions down. How many radians makes up a revolution? We are going to find that we have 2 pi rads making up one revolution. How do you get rid of minutes into seconds? Okay, I'll also say multiply by. So since I want to get rid of minutes, meaning that I'm going to put minutes on top. How many seconds makes up a minute? We are going to understand that we must have 60 seconds. All right. This definitely shows that we are going to cancel out this. We are going to cancel out that. I'll cancel out this, and also I'll cancel out that. What are the things that we are going to remain with? We are going to have radians on top of the numerator, on top of the over, and down here we are going to have what? Seconds. If you want to simplify everything, you can just say 20 here it goes 1. 20 into 30, it has to go 3 times. And definitely on top we are going to have 2 pi rads over, since we have 3 seconds here, I'll put it down here. I'll say 3 seconds. Okay. Calculator, very, very useful. So we are going to say 2, then you go on shift, pi over 3. Just deal with numbers because units are not even important at all at this moment of time as you are trying to calculate. So we are going to have 2.094, and the actual answer here we are going to get, after converting 20 revolutions per minute, we are going to get 2.094 farads per second, meaning that this is supposed to be the speed we are talking about. So whenever you've been given the initial velocity in revolutions per minute, the final velocity in revolutions per minute, what you should always be doing, you follow the same procedure of conversions. You are going to write it in this way: 20 revolutions per minute. To get rid of the revolutions, you have to put it like this. One revolution is making us to have what? 2 pi rads, meaning that radians are supposed to be on top, and down you are going to put what? Revolutions. If you come here to get rid of these minutes, you are going to put a minute on top. 1 minute is equivalent to 60 seconds. 1 minute is equivalent to 60 seconds. Alright. If we try to come to this given position, what are we supposed to do for us to understand what is happening here? You have to know how to convert degrees into radians, because those are the standard units we are going to be using whenever we want to calculate a question based on circular motion. Okay. So here I'll say, by the way we do convert degrees into radians, you find that 180 degrees is denoted by letter or a symbol 1. Okay, pi is equal to 180 degrees. As simple as that. As simple as that. So I'm saying pi has to be equal to that. How can you get rid of the degrees that are found here? How can we get rid of the degrees? So I'll say 320 degrees. I'll put them on top. That is per second. Alright. By the way, this is in radians. So we have to write like pi rads will be equal to 180. It has to be 180 degrees. It has to be 180 degrees. What can we do for us to get rid of this? We have to put degrees down. How many degrees makes up one thing? We understand to say pi rads makes up 180 degrees. Suppose we were given something like 320 degrees per minute, I would have continued up to the issue of removing the minute, which would have been down somewhere there. So since we this expression is just trying to tell us that we have been given seconds already, meaning that here don't even panic, just go direct into cancelling this and that. Okay, so you can do this. You remove 0, you also remove 0. Then we are going to multiply 32 by pi rads, and then 18 by the second, which is found down there. So definitely we are going to have something like this. If you say 32 multiplied by pi rads, you are going to have 32 pi rads over, if we try to multiply this and that, we are going to get 18 seconds equal to, okay. So I'll come here, I'll say 32, then shift, pi divided by 18. We are getting an answer as 5.59 rads per second. 5.59 rads per second. So these are the standard units for the velocity at this moment of time. That's how we do convert the same stuff. That's how we do convert these things.